In this video, we're going to discuss how to compute a dot product in terms of the components of the given vectors. So we're going to look at the component form of the dot product. I've drawn my two vectors here, u and v. We'll assume we're working in 2 dimensions, but the argument here works in 3 dimensions as well. It's just easier to draw and compute with fewer components. I'm going to label the angle between the two vectors. That's the smallest positive angle that's formed by those two vectors, and call that theta. And I want you to imagine u and v to form a triangle. And to get that side of that triangle, I'm actually going to label that as a vector. And I'm going to start at v here and go to u, although it really doesn't matter. I could start at u and go to v. But because of the choice that I've chosen of direction to go from here to here, this vector is u minus v. So you should think about u minus v as kind of closing off that triangle that they form. If this was a right angle, if theta was pi over 2, I could use the Pythagorean theorem to relate all 3 sides of this. But unfortunately, this is not a right triangle in general. That angle could be acute, it could be obtuse, and we just don't know in general. So instead of using the Pythagorean theorem, we need to use the more general result called the law of cosines from trigonometry. And the law of cosines says that if you sum up the squares of the sides, they're kind of related like the Pythagorean theorem, but there's an extra term that involves the cosine of the angle between the two vectors. And so that would look like the length of the side that is opposite the angle, in other words, the length of u minus v, and I'm going to square that, is equal to the length of u squared plus the length of v squared. So right now this looks like the Pythagorean theorem, but then there's an extra term in the law of cosines, and you take minus 2 times the length of the vectors that form the angle theta times the cosine of theta. And you can think about theta being 90 degrees or pi over 2. This entire term will be 0, and it really is the Pythagorean theorem. The law of cosines is just a generalization of that. We're going to use that, but we're going to express all of these quantities that involve lengths of vectors in terms of components now. So I'm going to take u to be u1, u2, v to be v1, v2. And we're going to compute now the squared length of the vector over here. So what do I have? I have u1 minus v1. I'm going to subtract that. u2 minus v2. So these are the components of the difference. And to get the squared length, I sum up the squares of those components. On the right-hand side, I'm going to have the length of u, which is u1 squared plus u2 squared. And then I'm squaring the length, so squared length, so I don't need the radical. And similarly, I have v1 plus v2. And then on the last term here, I have minus 2, but you should recognize this quantity here. The length of u times the length of v times the cosine of the angle between them is precisely what we define to be geometrically the dot product of u and v. So we'll have minus 2 times u and v. And now we have some equation that relates the dot product to all the components of the vectors. And we're just going to work with this equation a little bit and simplify it. And really, the only thing we can do is on the left-hand side, I can just expand these quadratic terms. So what will I get? I'll get u1 squared. Then I'll have u1 v1, but I'll have 2 of those terms. So it's going to be minus 2 times u1 v1 plus v1 squared. So that's just expanding out this term. You'll have something similar for this one. It's just everything's going to have a 2 on it. So u2 squared minus 2u2 v2 plus v2 squared. On the right-hand side, we have all the stuff that we had before, the sum of squares, and then this term involving the dot product. And lo and behold, lots of the terms will cancel out. All these squared terms appear on both sides, so I'll be able to cancel those out completely. And then what I'm left with is minus 2, this kind of mixture, u1, v1, minus 2, u2, v2. That's equal to minus 2 times the dot product of u and v. I'm going to cancel out the factor of minus 2 from both sides, and what I'm left with is u dot v are these middle terms in the expansion, the u1, v1 plus u2, v2. So the dot product of two vectors in 2 dimensions I get by multiplying their corresponding components together, and adding the results to get a scalar. If I'm working in 3 dimensions, if I have vectors with 3 components, I'm just going to add a third term. So it'll be u1, v1 plus u2, v2, and then u3, v3 for working in 3 dimensions. Let's look at an example. We're going to take the vector u to be 1, 2, 3, and I'm going to take the vector v to be minus 2, 0, 1, and we're going to find the angle between these two vectors. So I'm just drawing a rough picture. I'm actually taking some liberty here to assume that the angle between them is acute, but it could be actually quite large. I'm just drawing a picture for reference. Theta is the angle between them. We want to find that angle. The wonderful thing about dot products and thinking between the components in the geometric form is it allows you to figure out this trigonometric or this angular quantity all in terms of the components of the vectors and makes this calculation very straightforward. The first thing we're going to need is the length of the vectors. So length of u I get by summing up the squares, 1 plus 2 squared plus 3 squared, and take the square root of that, I get square root of 14 for this vector. Then we're going to find the length of v, so I get 4 plus 0 plus 1. Square root of that gets me square root of 5. We're going to need the dot product of the two vectors. So this is new now. This is what we just learned how to compute. U dot v in terms of components, I take 1 times minus 2 plus 2 times 0 plus 3 times 1, multiplying corresponding components, and all day I get 1 for the dot product. The fact that that is positive, and our previous discussion about the geometric definition, tells me that the angle between the two vectors truly is less than 90 degrees. It is an acute angle. We can now do better than that. U dot v is the length of u times the length of v times the cosine of the angle between them, and we can solve that for the cosine of the angle. If I do that, take my geometric form of the dot product, I get u dot v, and I divide by the lengths of u and the length of v. In this case, the dot product is 1, that's the numerator, and then I divide by these lengths, and I get a value now. This is the cosine of the angle between them. I can then go to technology and ask it for the arc cosine or the cosine inverse function of this quantity that we just computed. Using your calculator or software, you'll find that the angle now is 1.45 radians, or if you prefer degrees, it's about 83 degrees. Slightly less than 90 degrees. My picture wasn't too far off here. That angle between them is about 83 degrees.